Hello everyone, thank you for joining us for our Deeper Talks seminar. My name is Jared Heiss, I'm the Science Director at SURF, and I'm thrilled to introduce today's speaker. But before I do, I want to mention that along with all previous Deeper Talks seminar presentations, this talk will be recorded and available online on institute.surf/deepertalks, as well as on our YouTube and Vimeo channels. If you wish to receive a notification about future Institute events, sign up for our monthly newsletter at institute.surf/connect-us. Now it's my privilege to introduce our speaker for today. Dr. Robert McGehee is the Bill Fine postdoctoral researcher in the William I. Fine Theoretical Physics Institute at the University of Minnesota. Prior, he received his PhD from the University of California, Berkeley, and was the Lineweber Postdoctoral Fellow at the Lineweber Center for Theoretical Physics at the University of Michigan. He is a particle physicist who constructs models of dark matter motivated by direct detection efforts, hints from small-scale structure problems, and the genesis of the baryon asymmetry. I also want to mention that Dr. McGehee is participating in this year's SETUP workshop. SETUP is a Center for Theoretical Underground Physics in related areas, which promotes synergies between theory and experiment while exploring science conducted at laboratories worldwide. Now let's get set to learn about a moving target, direct detection in the light-dark matter landscape.
Good. So I thought it'd be fun to tell more of a story today. I'm not going to show you any equations, right? It's like this couple. But I want to paint a picture for you of what I think this light-dark matter landscape looks like, especially with regards to direct detection and various indirect detections. Okay? Good. But, of course, I'm talking about dark matter, and so I am obligated to include this slide, which at least I know many of you have seen 1,000 times. It's the dark matter slide. It includes all of our various evidences for why we know it exists and how much there is there. It is. However, I don't want to put you to sleep on my first contentful slide. So instead, let me just remind you of one of the key pieces of evidence, which is relevant for direct detection in the form of pictures. And this is based on the following observation. It's been known for actually hundreds of years, which is that further stuff is supposed to go slower. Okay? So what I mean by this is if we look at some galaxy, and we look at a couple stars here, the further star, which is further away from most of the mass in the center, is supposed to go slower than the closer to the star. Okay? This has been appreciated since the time of Kepler, and certainly was codified by Newton. Okay? Good. So we can go, and the royal we, astronomers can go and measure stars and gas to see how fast this stuff is moving and check if the further is going slower. And they have done so for decades, and what they actually find is that further things tend to go somewhere. Okay? So that's confusing. So if you're Rubin, for instance, in company, sort of making these kinds of plots all the way back in the 80s and even the 70s. So to just sort of quantify a little bit what I was just indicating, on the vertical, they're measuring the velocity of stuff in these galaxies. On the horizontal, this is the distance of the stuff from the center of the galaxies. And your intuition, again, from Newton and Einstein, pre-Newton, is that further stuff is supposed to start going slower. You could ask an undergrad in freshman mechanics exactly how it should scale, but it should be going slower. Each of these different lines is a different galaxy that they observe. And you can see that as you go out from the center of the galaxy, these things are not going slow. Okay? Good. So what is, right? What's the possible explanation for this this weird galactic rotation curve observation that was made now 45 years ago? Okay. Well, one possibility is, maybe these folks made a mistake. That is certainly a logical possibility, and this actually falls into the class of so-called modified Newtonian mechanics, ideas. However, I don't have a faculty job yet, and I don't want to be called a blasphemer, so this is not the approach that I'm going to take, and this is actually not the approach that most people take. Most people instead, due to accomplish other evidences that I had mentioned, think that the picture is the following. Galaxies are embedded in larger so-called dark matter halos, shown here as this nice blue, but of course visible. All right. And so all of this missing mass that we can't see, this dark matter, right, this is why the further out stars aren't going slower, because they're feeling the extra tug from all of this invisible stuff. Okay? And in fact, if we go and we measure a whole bunch of pretty galaxies, then you find that all of these have this sort of missing mass, which can be accounted for by this invisible dark matter stuff. Okay? So this is one of several things that get bulleted, pointed, or whatever on the dark matter slide. But this is the one that we care about for direct detection. So what do we know from this simple observation? Well, we know that there's lots of this dark matter stuff. It turns out there's something like 5 times as much as ordinary matter. And we know that it's in galaxies, including ours. Okay. And so from these two simple deductions, we can have a very simple idea. Maybe it bumps into stuff occasionally. It has to be very occasional because it really does look invisible to us. But maybe if it's extremely rare, but not never, we might be able to see it. Okay? And this is the idea behind direct detection, including an experiment that's, I don't know what direction, but relatively close under our feet currently. Good. So before I get into kind of the main chunk of my talk, which is sub-GeV direct detection, I thought it would be helpful to remind ourselves of what the landscape looks like today, broadly with direct detection. So this is a figure you may or may not have seen a million times. What we're looking at on the vertical is the so-called WIMP nucleon cross-section. So this is how much dark matter is interacting with nuclei. On the horizontal, we're thinking about dark matter that is sort of WIMP masses, it's 10 GeV and TeV. And we have a number of constraints from these excellent xenon-based experiments. None of these have found positive signals for dark matter yet. And so instead, what they have done is they have placed world-leading bounds all the way below sort of to the minus 46 centimeters squared, which is extremely high. So this is what it looks like today. What's the future of direct detection? Well, it's quite simple. You just kind of go off in orthogonal directions from this, right? So you can imagine going to lower cross sections or going to lighter masses. In thinking about going to lower cross sections, this is actually ongoing work, including here at SURF and at the mine, because there are several of these large xenon-based experiments, and they have been making progressive improvements and building up larger and larger exposures to get more and more sensitive to dark matter. So actually, I on purpose showed you a slightly outdated plot because after Xenon released this result in 2018, PanX released a result in 2021. This is not what I really have in mind when I think of moving target, but it's a complementary idea, which is that there's moving constraints you would expect. Okay, and then just a year later, actually, LZ released this quite impressive improvement in constraints, and Xenon came back a year later and didn't quite edge out LZ. So LZ, to my knowledge, is still the best in the world, which is great because I'm talking in South Dakota, so that's very cool. So LZ is still the leader of the pack currently. So really, this is sort of the present status. Direct detection for weak scale equipment. Okay. But I want to think about going lighter as opposed to sort of going to lower cross sections because lighter is kind of a challenging area. You can kind of intuit this just by seeing that all of these experiments lose sensitivity quite quickly below about 10 GeV or so. And you can convince yourself of this by sort of checking the kinematics of these experiments and appreciating that they all sort of have order KeV energy questions. Okay? So to go to lighter masses, you actually have to do something different fundamentally than using liquid xenon. And so this is actually an idea that's now also been around for a little bit. The idea is to instead look for dark matter scattering off electrons, because electrons are much lighter than, say, 100 GeV xenon. Okay. So this is, again, present ongoing stuff. So actually, the status of direct detection today is including looking at sort of the lighter dark matter using electrons, and for instance, the Sensei experiment, although there's many others, including CMS, okay. So this is actually the state of the art in the parameter space that I want to highlight today. So here we're thinking about dark matter that is sub-GeV, so from like sort of GeV all the way down to NeV, sort of electron masses. On the vertical, we're no longer thinking about dark matter scattering off nuclei, but instead of scattering off electrons. And now this is sort of the state of the art for the most updated Sensei constraints. You'll see that, number one, the cross-sections under the probing is quite a lot larger than what these much larger xenon-based experiments are able to probe. Okay, that's the first comment. The second comment is you might have a question, which is like, why is dark matter here? This might be a question that occurs to you sort of perhaps the first time that you see this kind of constraint plot. The answer is already on the slide, okay? But I just want to emphasize this is a question you would have because, for instance, this is not a question you would have in the other plot I showed you. So contrasting this sort of parameter space to the other one that LZ is searching for, there they even label the axes as like WIMP nucleon cross-section and WIMP mass, right? Because everybody's grandmother has known for decades that WIMPs are an extremely good benchmark, right? The gold standard for looking for dark matter via direct detection. We have a billion good WIMP models that live in that parameter space, so nobody has any concerns about why we're looking there. However, WIMPs can't live below a GeV, at the very least, we can't be scattered through Ds and Cs anymore. So you would like to ask the question, why is dark matter here? Again, the answer is right here. There's this cool orange line. So let's think about this a little bit, because it's going to be relevant for some of the models that I'll tell you about in a few seconds. Okay? So this was kind of the first target, arguably, for sub-GeV dark matter direct detection. What is it? It's a relatively simple idea. Friesen as a dark matter production mechanism was kind of formalized and named in this paper by Lawrence Hall and folks, although it actually existed in other guises all the way back in the 90s and Paul Garantinos. Okay, the particular iteration of Friesen, the particular model that's relevant for direct detection, looks like the following. You imagine that you have some dark photon, represented by this F prime here. It kinetically mixes with the Standard Model photon, and you charge your dark matter under this new dark photon. Okay, so just like electrons are very the Standard Model photon. And then what you can imagine is that because of this kinetic mixing in the early universe, Standard Model charged fermion pairs could annihilate through gamas and Cs to produce dark matter. And if the coupling is actually quite small, then it turns out that this process really is unidirectional in the early universe. It only proceeds in this way if you assume that after inflation, you don't have too much dark matter. Okay, so if inflation does not produce much dark matter, you start with negligible abundance. Then this kind of Friesen process can occur slowly, and build up your dark matter to get the amount that we observe today if the coupling is this talking about. Okay? So then you can say, could I possibly see this thing? And you could, instead of thinking about the final diagram this way, you just rotate it by 90 degrees, and you imagine dark matter scattering off electrons, for instance. And this is a kind of cross-section that you can then go and search for, and indeed that's what this orange is. Okay? So, it's a relatively simple story. It may be slightly more assumptions than sort of when Miracle frees out, but still relatively minimal. And a good target. It's a nice line to shoot for. However, you can tell it's kind of a future target, right? At least in looking at this constraint plot, because, all right, there's some parts where maybe it's an order of magnitude off. However, at these sub-GeV experiments, backgrounds are extremely challenging, and building out larger exposures is not so quick and easy. So one might imagine, especially if there's from the outside, that this might take some amount of time to hit this. Okay? But there's an asterisk on purpose so that people can wait for me to talk about the asterisks. But for now, we'll think of it as a future target. So a question that you might have then is, okay, we have one good target. We've known about this target now for over 10 years, all right? We've started building experiments looking for this target. But are there any current targets in the meantime? So I just see like a single line here. Good, so this is going to be my first iteration of what I call a moving target. This is work I did with folks in Michigan. So it's going to be actually a quite simple modification to this Friesen story I just told you. So we're going to have the Friesen model I told you about, and we're just going to add one new light fermion. Okay? Let's actually take it to be massless. It doesn't have to be, but for simplicity, let's say we have a massless fermion inside. And its sole purpose in life is going to be to interact with it. So I took the model I told you about, I added one massless fermion, and I added one set of interactions with okay. The reason I do this is because now, instead of having this quite small coupling, you can imagine instead that a range of couplings could still be consistent with the observed relic abundance, because intuitively, if for instance you have a coupling that's a little bit larger than what Friesen would like, you can just sort of, kill a little bit of the dark matter thanks to this second process switch example. Okay? So it turns out that you can get actually quite a range of couplings here, many orders of magnitude potentially larger than the freeze-in case. And the result is that you can have larger cross-section at current experiments. Okay? So getting back to this parameter space we're interested in, down here we say, okay, here's our freeze-in line that we're eventually going to target, and then Sensei and other experiments are targeting. I have bothered to also flesh out the other experiments that are putting constraints to this part of parameter space, as well as sort of CFB constraints. We also corrected a slight error in the old freeze-in line as they're run for forever. So everything that you see in red here is sort of dark sync parameter space. This is all where we have consistent cosmology, we have right relative abundance, we avoid all the other constraints, and it's just thanks to this single sort of new massless fermion, so-called dark sync, which is permitting you to get the right abundance. Okay? Cool. So again, freeze-in is kind of a future target, and dark sync is our first iteration of what we'll call a moving target, namely it's some consistent, relatively minimal amount that we're testing in the meantime as we get to the freeze-in line. Good. Now I can tell you things that are relevant as of 2 months later. Okay. So this asterisk was doing a lot of work, and some of you, I'm sure, I've told about this or saw on your own. Okay. Freeze-in was a future target as of March, but then on March 18th, this came out. Okay. Pause for dramatic effect. Yeah. So Damakim is one of these competing experiments. In fact, I have them down here. This is one of their old results. Okay. They are also using the same technology as Sensei. They are also using the so-called sticker CCDs. And they came out and they blew through the freeze-in line. I believe to my personal surprise, to surprise a lot of theorists, and also my understanding is to the surprise of some of these other experimental operations, they blew through the freeze-in line for the first time. Okay. This is incredibly impressive. They made multiple sort of order of magnitude and larger improvements to be able to hit this line for the first time. And it was extremely exciting, okay? So now they're testing freeze-in from sort of few MeV all the way up to several hundred MeV. And this is not even, the final iteration of this experiment. They will have new results within, hopefully, 2 years, maybe even less, okay? So this is incredible, all right? Good. This was a question that kind of occurred to me immediately when I saw this result. So if you look at this parameter space, especially as a model builder and a theorist, and you stare too long, you might think that this represents a little bit of an existential crisis for direct detection. So let me now pivot at this point in the story and pose a very bold question for us to all consider as an audience. Okay? The question is the direct detection program, due to its great success, barreling towards an existential crisis? Now, I should highlight great success. Really, due to its great success is a very non-trivial clause in this question. Okay? But this is maybe a question that would be interesting to think about, especially given these recent steps. Okay? So, I am posing it as a question. I don't want to pose it as a statement. I want us to all think about it together. All right? And with such a bold question, I think that I should give quite a bit of context and quite a bit of evidence, maybe in the affirmative, and then we'll sort of recap. So what's the context? Time for an obvious statement, but it's a useful one to remember. The direct detection program exists because highly predictive theories of dark matter exist. Okay? This is in contrast to, for instance, indirect detection and collider switches. So the other two ways that we typically look for dark matter, these two ways exist independent of looking for dark matter. In other words, X-ray astronomers don't give a crap about the model that I'm building of dark matter that may or may not show up in their X-ray telescopes. They want to do X-ray astronomy. Likewise, the LHC was not funded to look for dark matter. At its inception, the bullet points of sort of ESM physics targets did not include dark matter, right? Now they do. They didn't originally, and they won't even. The LHC program will continue regardless of the positive signals of dark matter. Okay. This is qualitatively a different situation from, at least historically, why direct detection is existing. Okay. I should also clarify what I mean by highly predictive theories. Again, I'm just going to say obvious things, but I want us to all be on the same page. What is a highly predictive theory of dark matter? It's something like this. The original papers by, for instance, Goodman and Witten proposing direct detection as a possibility. These kinds of papers that started being written in 85 and onwards, they were all talking about well-motivated WIMPs and why eventually, yeah, if we build a big enough thing, we beat the background down, we might be able to see these. Okay? So this is the gold standard that I have in mind when I think of highly predictive. In other words, the thing that explains the relic abundance also tells me where and why to look for it. The right direction. Okay. Good. So getting back to this question, let me actually rephrase it slightly. Okay. Is the direct detection program, because it is testing below highly predictive theories of dark matter, losing its whatever this French word is? I was in Paris and I wanted to be fancy. I still have not figured out how to pronounce this, and I will probably never. But anyways, I think you guys will be in this. Good. So now let's maybe go through some evidence, possibly to the affirmative of this question. Again, just for us to all sort of appreciate the situation. Okay. Exhibit A is something that I've already shown you and that we're all familiar with. Namely, if we're thinking about sort of wimpy masses, the status of the program is that we are pushing through a lot of our highly predictive targets. Now, there are WIMPs that are still lower, so we have not reached all of our highly predictive dark matter targets, and we should continue to push lower as we're trying to reach this, okay? But this is just to say that we're pushing towards the so-called neutrino fog, and we are continuously probing more and more of our favorite WIMPs. Again, gold standard, okay? Exhibit B is actually another figure from this impressive paper, which I haven't shown you yet. So in this slicing of parameter space, again, sub-GeV dark matter scattering off electrons, but now we're analyzing their data in the context of not scattering through a light-yard photon, but instead scattering through a heavy mediator. In this situation, there is actually a nice freeze-out benchmark, so equivalent to the WIMP miracle, but just not using weak scales. This, for the first time, has now been fully probed by Damakian. Okay, they have fully probed freeze-out from 1 MeV, where you can't go lower because of BBN, all the way up to several hundred MeV with this simple freeze-out line. And then Exhibit C is the thing I already showed you. Okay, but let me actually emphasize a few points now. When you go below the freeze-in line, you are de facto decoupling why we are looking for dark matter from the one thing we know about it, which is its abundance. Okay. So that's a sort of profound statement. It is not a proof. Okay, this is just an intuition from the simple model building. This is not a proof. Okay, and in fact, I'm trying to think of lots of ways to break this statement, but this should be vaguely your intuition. Okay, this is the first time this has happened. This has not happened previously, for instance, in looking at probing WIMPs, as we continue to still have good WIMP targets. This is really the first time direct detection has ever done this, where intuitively you are thinking that you're probing below a region where maybe you don't really have this cross-section influencing. Okay. And it's therefore some kind of term. Good. So getting back to this question, let's reframe it. I think that this is not necessarily a crisis, right? That's maybe a bummer, and definitely not a nice way to start Wednesday. I think it's actually an opportunity. Okay, I think it's one that, in some sense, still feels existential, but we should interpret it as an opportunity. All right. Good. So getting back to my comic story, at this point in our story, crisis is just a term. Right? This is what all good stories have. They have a crisis. It's bad. Terrible stories end at the crisis, and then you're left feeling like, why did I pay one for this movie? Good stories, this is just okay. So this is what we should do. Now that we're at this turning point, this is also what I have in mind when I said moving target in the titular slide. Short term to long term, I'm going to tell you my personal bias perspective, so maybe what theorists could be doing, but also a bit what we should be doing in the broader direct detection community. First and foremost, I think that it is still very worthwhile to construct dark matter models which predict signals given the current constraints and the current landscape, what we're able to test, what we've already tested. Okay? I was giving a talk actually just a few weeks ago, and my friend and colleague at Fermilab was in the audience, Gordon, and he said, well, I have one quick comment for you because, this is not the end of the world. There's actually still simple models that could be tested. And actually, it was amusing because he put out a paper the day after my talk, so he had already submitted this, and he was like, yes, but this idea, and I was like, Gordon, did I not read your paper? Where he said, and it was like, oh, it's... So, Gordon also thinks that this is a good idea, and actually it's quite cute, even in the very first bit of this abstract, he is thinking very much in the context of these Dom game results, and then going on to think about all sorts of model building games. So, what is a minimal model from Gordon's perspective? It's actually quite straightforward. You take this result line that I showed you a few plots back that Dom has now ruled out. But now you just imagine that the mediator is not quite so heavy. So this R here is the ratio of the mediator mass to the dark matter mass. If the mediator is heavier than about 3 times the dark matter mass, you get this single curve, which is pretty sound, okay? But as you start bringing the mediator mass down and closer to twice the mass, you start hitting a resonance in the early universe, okay? And it turns out that you therefore need a smaller cross-section. And so you can sort of scan out from the currently pulled out line all the way down to the eventual neutrino fog by imagining that you're scanning through the masses. Okay? So, relatively minimal, you start with the model that you already had in mind, and now you just imagine maybe going into this slightly fine-tuned, but not really crazy fine-tuned. That's one reasonable idea. Good. What's other things that we should do? Find new use cases for these incredible experiments. That kind of goes a little bit without saying, but especially for theorists, I think it's a good thing to mull over. In terms of broader direct detection community, now especially that we've pushed through freeze-in, we've pushed through freeze-out for sub-GB, it would be great to agree on some set of new benchmarks as a community. This is really where we could shine and make some amount of progress to come together and decide, here's what we're gunning for, right? We already hit the thing that was a good idea for 10 years. What else is left, and what do we think is exciting? This kind of goes without saying, but especially for this audience, I should really emphasize it. We should reach the rest of the WIMPs. We should continue to go LZ, bigger, better, go all the way down to the neutrino fog. At least the WIMPs are the gold standard. They're still the gold standard, even though I don't do the model building for them. They're the gold standard, right? If WIMPs were discovered tomorrow, I would be ecstatic. Right? That I had written all these silly papers that don't matter. That would be amazing. I love it. Good. And finally, maybe the hardest thing to do, okay, but definitely should be included and at least thought about. Discover new dark matter and experimental paradigms that sort of throw away a lot of the assumptions that I made on the previous slides. Okay. Good. So now that I have maybe 5 minutes, okay, 5 minutes, I will very briefly highlight some actual work that I've done instead of rambling on soapbox what the present state of things are. So I've already told you about dark-seek dark matter. I'll really quickly throw up a few slides on some other models that I've been doing that are hopefully interesting. A caveat to this sort of existential crisis, or rather existential opportunity, this dynamic result is really only talking about dark matter scattering off electrons. So if you have light dark matter that's hadrophilic, or coupled really primarily to nucleons, then okay, this dynamic story has nothing to do with it. All right, this actually is still a very experimentally challenging thing to look for, but it's a very active area of research. It's very exciting. There are ideas about using supersonic helium, for instance, and collaborations that are starting up and going in this direction. So let's look at some cool models maybe for this sort of parameter space. The first is the so-called hyperdark matter. That has an acronym. I could tell you, but it doesn't matter. Okay, it's just supposed to be extremely interactive dark matter. Why we call it vectors. So in this sort of model building game, we wanted to try to get as large a cross-section as we could consistently with all of the other known bounds, as well as getting the right relic abundance, for a number of reasons, but one of which is to see how these future experiments might stack up relative to a sort of pie in the sky theorist model for very large cross-section. So what's the cosmological story? At early times, we do a version of Friesen called UV Friesen. If you're interested, you can ask. At later times, there's a phase transition, which causes the mass of the mediator, in this case, to drop significantly. The result is that the direct detection cross-section can be much larger than you would naively expect. Okay? There's all sorts of things you have to be careful about. As a model builder, you make sure you don't muck anything up when you do the phase transition. But we made sure that we were careful, and the result is the following. Everything in blue is a viable model of this so-called hyper-dark matter that gets to relatively large cross-sections. We're thinking again about sub-GeV sort of parameter space, but now scattering off nuclei and not electrons. Everything in sort of dashed gray here is all these ideas. None of these are current experiments, these are ideas that people have about what we might be able to probe, hopefully in the next few decades here. So this sort of hyperspace is a nice sanity check, among other things, for all of these ideas, because you see that when I really try to dream up some model that has a quite large cross-section, all of these ideas are sensitive to it by several orders of magnitude. If it was the other way around, it would have been like, it's not so great. But they are, so cool. Maybe that's interesting. An even simpler idea is actually to do this UV Friesen, but don't even have the phase transition at all. Just imagine that after inflation, the reheating of the universe occurs at a relatively low temperature. If you do this, then dark matter can really only be produced through loops off of photons because there's nothing else in the standard model that left. And the result is that you get cross-sections that are not super, super large, but they are, to a large power, sensitive to the reheating temperature. And so you might think, hey, maybe for low enough reheating temperatures, this could be an interesting benchmark as well. And this is what we find, again, looking at sort of sub-quantum mass dark matter, all of the dash rays, all of these various ideas. You don't get nearly as large a cross-section as I showed you for hypers, but we're not doing the space transition game. We're just assuming that we have low reheating temperature. So all of these different contours is not this UV Friesen scenario, but just with successively lower and lower reheating temperatures, and you see that, okay, if you're willing to dial down the reheating temperature sufficiently, okay, then you can imagine some relatively minimal consistent scenario as a future target for these future experiments. Okay, good. All right, so now that I'm out of time, I will just flash up very quickly one idea that my collaborators and I have had along the second point here, which is new ways to use these experiments. This is the kind of dark matter we call fermionic absorption dark matter. The idea is very simple. We said, what if dark matter wasn't stable? If it's not stable and it's a fermion, then all sorts of interesting things can happen. In particular, dark matter could be absorbed by standard model targets like electrons or nuclei, and other junk could be kicked out. So you could have neutrinos coming out, or you could have electrons and positrons coming out. Okay? This is quite cool because all of these signals look very, very, very different than elastically scattering WIMPs or elastically scattering sub-GeV stuff. Okay? In particular, the top processes typically lead to very peaky recoils, and the bottom processes you get like way more than you bargained for. You can see the outgoing electron or positron potential. You can see the excited nucleus and de-exciting. You can see the kick of the final nucleus, etc. Okay? So I don't have time to go into this. Ask if you're interested, but I'll just highlight that we convinced, fortunately, a lot of our experimental colleagues to start going and doing these searches with their existing data. So this is a case of getting the most bang for your buck. Right, where they have the data, but you just need to do a new analysis for this kind of wonkier dark matter because the signals were quite different. So PandaX has already done 3 searches now looking for absorption off nuclei and electrons. Majorana has done one for nuclei, EXO 200 as well. CDX has done nuclei and electrons, and Pico has done nuclei. These are all various iterations, and if you're interested, you can ask. They use 2 different Lorentz structures, slightly different operators, etc. But the takeaway is that this is now very active, exciting thing. Okay, good. So I should wrap up here. This is what I think we should do now that we find ourselves at this existential opportunity turning point. I've fortunately been working on a couple of these things, but I'm very interested to talk about any of this stuff with folks. Good. That's it. Thank you.
Well, that was a fabulous journey on a very timely topic. Let's open the floor for questions. Maybe starting in the room. I'll run my microphone, or do you want to run mic?
Just sort of a fun question to go back to the first half of your talk. I wonder if maybe we have been at this juncture where we push below a set of well-defined, well-motivated models before. Specifically, I'm thinking about in the 90s, and I'm not actually sure exactly which experiment did it. But at some point, a very simple WIMP with a spin-independent cross-section of 10 to the minus 39 centimeters squared, like you'd expect if it, had a direct exchange with the standard model through a Z or a W. This was pushed past, I think, in the sort of early Zeppelin dark matter searches. So I guess what I'm saying is, in this sense, maybe the crisis isn't new. So I was just wondering if you have thoughts about that.
Yeah, no, so that's definitely a fair point. So, so it depends on, what you think of as a opportunity as opposed to a crisis. But, so certainly maybe some of the largest cross-section cookie cutter WIMPs got pushed through quite a while ago. In my mind, at least, because I sort of already grew up with that as a prior, I've always still thought of there's still WIMPs to go, and there's still very reasonable, very minimal, anybody could write this down WIMPs. And so, at least for me, in the sort of WIMP mass range with these liquid xenon experiments, they've continued to push, and this has always for me just been like, yes, we're going through all the WIMPs, but I haven't. For me, it hasn't seemed as much like a crisis thing. At the very least, I would say, for the things that I thought about, which has mainly been sub-GeV, this is now, for me, feels like quite a turning point now for sub-GeV. So whether or not, you felt or didn't feel like this in the WIMP mass range, maybe a long time ago, or just currently, or maybe in a few years, this is at least the first time for sort of sub-GeV where we did the thermal thing, we even did the reason.
Yeah, and we could talk about minimal WIMPs and how minimal they are.
It's called things.
Other question in the room here?
Yeah, sorry. Thanks for the great talk. I have just a naive question. So in all of these sub-GeV dark matter models, I mean, have people have tried a bit, but have they tried to put this in a more UV complete models where you also try to solve other problems like WIMPs, for example, right?
So for instance, I didn't highlight any of them here, but I've got a number of papers, just myself. This is a very simple idea that a lot of people have done, which is you do effectively sub-GeV or maybe GeV-ish model, but if you couple it, you make it asymmetric dark matter, and you couple it to some varieties. So that's a very, very straightforward way that a lot of people think about GeV scale dark matter that is coupled to another problem. Or, for instance, if you think that you would like self-interacting dark matter to solve some of these small-scale structure problems that we have hints of, that is another sort of existing problem that people have looked. You really want light dark matter in that case as well. So, for everything that I've sort of discussed here, I was really just focused on let's think about direct detection and blah blah blah. But there are a number of other pieces you could go on like this with.
Thank you.
Other questions in the room or online?
We have one here from online. Besides the neutrino fog, what would be the biggest challenges of our current technologies that, in your opinion, should be prioritized for pushing our sub-GeV sensitivity?
Oh man, that's a great question. That as a non-experimentalist, I'm totally unqualified to answer. So I want to know the answer to that question as well. For sub-GeV, my understanding is that maybe exposure is a little bit of a challenge, just in that, tabletop is easy, but maybe scaling sizably larger than tabletop is perhaps not so easy with these skipper CCDs. That would be one thing that I would naively say. Prior to Dominick's amazing result, I would say the backgrounds are really quite tricky, but Dominick has now implemented a number of improvements relative to prior experiments, including themselves, which have fixed a lot of this. So, I would say exposures. I would also say the sort of future things that I was talking about with this hadrophilic dark matter, all of these are going to have challenges in the form of they don't exist, they'll exist for the first time, and backgrounds are going to be whatever the backgrounds are. So that will be a whole new R&D direction for each one of those different ideas, whatever it is. That'll have challenges when people start building it and measuring.
I just want to note that question came from Sophia Hollick, just to give her credit for that excellent question. We have another one, and she says, awesome, that's exciting, thanks. We have another one from Chad Ronish. For detection of sub-GeV dark matter, is it safe to say that we would be looking for energy release from uncoupled fermions, or are there specific particles that would be created?
Oh, so, yeah, good. So in sort of most of the usual direct detection, not just for sub-GeV, but also for WIMPs, what you're looking for is just dark matter coming in and kicking your target. So in the case of sub-GeV dark matter scattering off electrons, what you're looking for is electrons that have gotten kicked. So no creating of particles, anything exciting like this. You're just
Other questions, comments in the room or online? One there.
Thanks for the great talk. How theoretically challenging is it to come up with some model for dark matter where you have this a dark matter particle plus some other stuff that is only interacting with the dark matter and gravity, and then you end up with like the dark matter fraction being like 0.1%, and then you just scale up your cross sections by 3 orders of magnitude.
Good. So I think if I understand correctly, you're asking what if you just have some situation where you can predict a subfraction of dark matter and therefore get larger cross sections? Yeah, that's probably not super challenging. That's probably something that you can do. As with a lot of these model building games, the name of the game is sometimes a little bit aesthetics, and so sort of the whatever minimal number of assumptions that you can do, which result in something, will mean that it's the more minimal it is, the more that people reasonably sort of care about it. And so it's just a question of that. Typically, people work with 100% dark matter for this reason. But yeah, you can start doing stuff with subfraction dark matter and then immediately effectively get a larger, or rather smaller section. But there you enter, I would say the only cautionary tale there is as you start explaining less and less of all of dark matter, you fall into the decoupling the number that we know from why we're looking. So if you have a convincing story for 10% dark matter, great. But if it's a convincing story for 0.1% dark matter, then...
Other questions in the room or online? One quick thing I'll follow up on with the DOMIC-M and possible future improvements. There's a connection here to SURF. Some of the electroform copper that the Majorana demonstrator collaboration produced over many years has recently been procured by that collaboration. Also, some of the very pure lead. So,
nice.
Lowering backgrounds for that experiment in France has a connection here to SURF. So that's really interesting. One other question I had quickly: a lot of the models that you showed on plots had masses that extended to maybe 10, 100 keV. Do the models extend below that?
No, they don't, and on purpose. So below sort of 10 keV or so, you can't have fermionic dark matter. So just don't. There's just pressure in both galaxies. So if you have a fermion and you go to sufficiently light masses, then you blow out the dark matter in the smallest scales to be measured by. You just can't.
Any last questions before we wrap up? Right. Well, thank you again, Dr. McGeehee. So, quick reminder, this talk is available to view and share on YouTube and Vimeo, as well as on our Institute website, institute.surf/deeper-talks. Next month's Deeper Talks will be on July 9th just ahead of Neutrino Day. Same time, same place, 9 a.m. Mountain. The topic will be solar neutrinos, history and observations with featured speaker Aldo Oyani, who's been a friend of underground science for many years, has been here once before. He's joining us again in July. Your feedback helps improve this program, and we appreciate any suggestions for speakers or for topics for future talks. Please fill out the short survey at the end that you'll see on Zoom or in your email. And with that, we'll wrap up. Thank you again for those in the room and for those online for attending. Take care.